Well, Bob MacDowall wasn't able to be here today, so indeed I'm Dayton Jones from JPL. I'm giving his talk for him, which I presume will be up momentarily. We heard earlier this afternoon from Joe Lazio that there's multiple reasons for wanting to do low-frequency radio observations from the lunar surface. And some of the most interesting and exciting of those reasons, such as the cosmologically important observations of neutral hydrogen from very, very high redshifts, very early cosmic epochs, require very large numbers of antennas, and consequently it's critical that antenna mass be extremely small. And that's the motivation that led to odd ideas like this idea of making antennas out of conducting films on thin sheets of kapton. And that leads naturally to the question of how do you employ something unusual like that? So this is essentially a status report on work that's been led by Bob MacDowall on one approach, a fairly simple and straightforward approach to deploying long films of kapton on the lunar surface. It's right. Next slide, please. Next slide, please. Okay. So this is essentially a deployment scheme that's designed to be compatible with a simple precursor mission, the sort of payload that could be a secondary payload on a small lander, and therefore something that could fly in the fairly near future, potentially. It's Joe showed part of this concept along with some of the other things that are being investigated, like inflatable tubes that would unroll across the surface. This is essentially a ballistically deployed anchor, which then is used to reel out film, and I'll show a couple of videos of how that works in a moment. Next slide. Okay, and this is just, you've seen this also from Joe, but this is one of the things that this can lead to in the intermediate term, one of these low-frequency arrays with an intermediate number of antennas that could do imaging and tracking of solar radio bursts between the Earth and Sun. Next slide. And consequently could do things like localize the emission regions and therefore tell us something about the particle acceleration mechanisms behind radio emission during energetic solar bursts. This the diagram in the lower right there is simply a schematic view of what a station like this might look like with an electronics box in the center and arms of kapton going off radially. Next slide. But there's things you could do with just a single antenna, and this is something that a very simple precursor mission could accomplish. On the single antenna, you can still measure radio spectra, and consequently, you could look for evidence of low-frequency absorption by a lunar ionosphere. The figure on the left, although very old, has been shown in countless talks about the moon along the way, and it indicates that there is evidence that on occasion, at certain sites and certain epochs, is a significant lunar ionosphere, large enough in electron density to affect low-frequency radio observations from the lunar surface, certainly at frequencies of a megahertz and below. An ionosphere of the sort indicated there for 14 May would be a really serious constraint. So we want to get real data on this over a long period of time and see just how reproducible this is and what the statistics are. And of course, the related thing is once you've got anything, any large radio antenna deployed, you've also got, by default, a good dust detector. And these sorts of antennas provide a very substantial collecting area for that kind of data. Next slide. Okay, so this is the basic idea. You spring launch an anchor, and there's a little indication there at the bottom of what such a thing might look like, from your package out as far as you need to go over the lunar surface, and it's trailing a small wire, two small wires, which you then use to pull out this thin metallic antenna. And the next slide indicates the overall scheme here. This is the basic test setup, the electronics, and this is the harpoon-like anchor as it's being prepared for launch. This gold cylinder here is the spool of Kapton that's going to be deployed. This is just a laptop and a wireless transmitter that controls the entire test setup remotely. And this is just a close-up of the anchor in this crossbow arrangement and the spool of wire that's going to deploy there. And you can just see a little bit of the Kapton roll there at the bottom. So the next slide should be the first of 4 movies. If we can get the movie to run, this is fairly quick, so you have to watch closely. It will fire, and you'll see the wire unspooling there for some time. There we go. Okay, and then the next one, please. Next slide, that is. Yes, okay, this one will show the wire rewinding. This motor here is driving this spool backwards. You can see the wire here being drawn in. And the next one, please. This next short video shows the beginning of the film deployment. And yeah, right at the very bottom here, see right there, you'll see in a moment that it lays out and then it starts to move sideways. The final video just shows the antenna moving slowly across the surface. That's one of these videos, I promise. We go to the next one. Yeah, that's it. So you can see here, if you look carefully, you'll note that this is moving. It does not move with breathtaking speed, but it does get there. This is the anchor here, doing its job of sitting there inertly. And this is essentially exactly what was intended. Obviously, this is a fairly benign, fairly smooth surface, and one has to test this over much more difficult terrain, but it's a promising beginning. And if we can go to the next slide. This just goes on for a while, but it's not any more exciting than this part, so we can skip the rest of it. On to the next slide. System reboot. Okay, very good. There are failure modes that we probably are not going to have to concern ourselves with too much in an actual lunar deployment, the most serious of which turned out to be wind, which picks this stuff up. It's very light. It picks it up with extremely minor breezes. So one can avoid that by testing things indoors, where of course the deployment is virtually perfect. I rather doubt that Bob shot this deployer inside the conference room and embedded it in the wall, but he sent me an email just earlier today saying that he has just tested this in the centrifuge room at Goddard, which I suppose is large enough, and finds that the anchor hangs onto little cracks in the concrete floor very successfully, and you get this kind of beautiful deployment in there as well. So on to the next slide. So this is basically one of several concepts under development. It's nice because it's just so straightforward. There's other things being considered, including rovers, both autonomous rovers and human-controlled rovers are both possibilities, and the sort of inflatable tube concept that Joe showed a video of during his talk. And they all have pluses and minuses, and probably other innovative ideas will come up as well. But the bottom line is there are multiple fairly straightforward ways to deploy a scientifically very valuable instrument from a small package that could fly shortly as a piggyback payload on any of the next generation of lunar landers. So I think I'll stop with that. Thanks.
We have time for one question.
Once deployed, you run the potential that you're going to end up with dust starting to build up on the surface. And what problem, if any, does that pose to you?
It's actually not a problem at all. I mean, lunar dust is essentially non-conductive, and you could take these antennas and coat them with dust, and it would have no electrical effect. That's a fortuitous circumstance.
Any other questions? All right, let's thank our speaker again. All right, next up we have Jordan Moroka talking about disentangling the assembly history of